Thanks. So I guess I should start with a caveat that even though this is the turbulent section, this talk might fit more in with circulation or some other sections of the conference, but in the spirit of it being multi-scale and connecting all the different aspects of the Southern Ocean, I thought I would go forward anyway. So this is some work that some of you in here may have heard me talk about before, and for those who haven't, I'll try to make sure I cover everything and not forget. This is work that I've done through the Australian Antarctic Program Partnership, and it's a large international collaboration with Steve, Sarah, and Natalie, Tayo, Jean-Baptiste, Esme, and Luke. So there's people from Japan, the US, France, Australia, and oops, sorry. Okay, now I don't have to see myself. And so it's using a pilot array of deep Argo floats to look at the water mass properties of Antarctic bottom water and the circulation pathways in the Australian Antarctic Basin, which is just south of Australia, near Antarctica. And so I think a lot of people in this room know how important the formation and export of Antarctic bottom water is. Forms the lower limb of the meridional overturning circulation. It fills up a vast majority or a large majority of the ocean basins, and it's formed in these sort of discrete regions around Antarctica. So there's some formed in the Weddell and the Ross Sea along the Adelie coast, and also over by Cape Darnley. That's not on this map. This is a map of mean CFC concentrations in the deep ocean, done by Alex Orsi and others in '99, and it's showing that there's in the Australian Antarctic Basin, which is this outlined in red here, it's actively ventilated. So you see those high concentrations of CFCs from those two different source regions, one coming from the Ross Sea and one coming from the Adelie land near the Adelie Depression. And so CFCs are a chemical that's in the atmosphere. So it reflects that those blues have been recently in contact or in communication with the atmosphere. So you could imagine that a map of deep oxygen would look very similar. So active ventilation from those two different sources. We also know from repeat hydrography that the Antarctic bottom water there has been warming rapidly. And so this is a map from Perkey and Johnson in 2010 that shows strong warming, especially around Antarctica, and actually the strongest warming in that Australian Antarctic Basin. The data that goes into making a map like this, come from these kind of fainter lines across there where they do repeat hydrography at least once a decade is the goal, sometimes more frequently, but as you can see, the data are very separated in space and often separated in time by quite a few years. And so as brilliant and amazing as this picture is, and it tells us a lot of information about changes in the deep ocean, it's based on relatively sparse information. And if we look closer just in the Australian Antarctic Basin, this was work by Esme and Steve, and they used these lines on 150 and 140 and kind of 115. These are repeat sections that went into making this map, and some other data that came from L10 and voyages in the late 60s, early 70s are those yellow dots. So they put together this map to look at the inferred circulation, and they see as you go away from the two source regions in the lower right-hand corner, you can see the Ross Sea bottom water by 160 and the Adelie land bottom water by 140, making this clockwise circulation pattern around the basin, and that the warming gets quite strong as you go farther along that circulation pathway. On the other hand, if you look at that same map there on the right, the freshening is very strong near those two source regions of Antarctic bottom water. So when dense shelf water is formed on the shelf and then exported down to mix with circumpolar deep water to create Antarctic bottom water, that freshening signal is very strong close to those two source regions, which is thought to be driven by glacial meltwater input on the shelf. This study came out in 2014. Since then, there have been some rebound in the salinity of the Ross Sea bottom water specifically, but just before, you can also look at these patterns. This is along 140. So this is this line here, that SR3 line that has been occupied, one of the most frequently occupied of all those repeat sections by a lot of hard work from people in this room and others. And you can see that strong freshening. So we have salinity on the x-axis and temperature on the y-axis. And you can see from the I'll just call it the 70s through the 90s and 2011, the strong freshening and also some warming in those deep, dense layers of the ocean. Along 150, which is right at the sort of the closest to the mouth of the Ross Sea bottom water source, you see a similar picture if you look in the colors. So you see this freshening from red to blue to purple and these orangey browns. And then in 2018, there was a strong rebound in that salinity of that dense bottom water. So this kind of pink line there, you can see the rebound of that characteristic salinity tail. And I will use that later in the talk to infer pathways of the two different bottom water sources or flavors of bottom water. And then in 2018, a pilot array of these deep Argo floats was deployed. So here are data, this gray and black are data from those floats right near 150, very close to where the CTD stations are here, showing that the 2018 is basically the same time as that voyage, because that's when they were deployed. And then 2019, you see a continuing of that rebound of salinity, which speaks to how the different properties on the shelf might be changing or the amount of export might be changing. But we see this rapid and at the time quite surprising increase in salinity of Ross Sea bottom water. And Alessandro Silvano did a paper looking at some of the drivers of that rebound and found that it was an anomalous large-scale climate modes that changed the winds on the shelf, that changed the sea ice distribution on the shelf, which then drove stronger polynyas and more brine rejection and more salinity. So it sort of, that signal propagated all the way through. Okay. This is the array of floats. So this was deployed in 2018. There were 12 floats in the array. Some, depending on their model, some can profile down to 6,000 meters, others can profile down to 4,000 meters. But most of the colored little symbols on this map are full depth profiles in this basin. And this data is just showing the first 2.5 years. Most of them to try to match the core Argo and have this sort of one Argo vision of the world with deep BGC and core. After initial testing, they start profiling 10-day cycles. They have deep parking pressures, so you can set the different pressures. And so most of them, aside from this one, most of them were retained in the basin and didn't get swept away by the eastward flow of the ACC higher up in the water column. They also have ice detection algorithms built in so that they, if they sense that there's sea ice as they are profiling upwards, they will stop and turn around and not just crash into the ice and hurt themselves. So we have under ice profiles for a lot of for whenever there was ice, which is very exciting to have full depth winter profiles. It's very hard to collect that sort of data from a ship. The locations when they're under the ice, you might imagine they can't talk to the satellite, so they don't know where they actually are in space. You only have the first profile before winter and the last profile after winter. But Luke Wallace and Esme and others developed this algorithm to use both the bathymetry data and the maximum pressure data to do a more bathymetry following interpolation of the locations for the under ice profiles. So it's better than a straight line, which is the next best thing, really. We took CTDs on deployment of each float so that they could be calibrated individually. I think that's all I need to say about the floats. Does anyone have any questions before I move away from the technical stuff?
How long does it take to come up from 6,000 meters?
How long?
Yeah.
I think like a couple hours. So there are profiles that I'll show you later when one of the floats was still in its initial testing phase that ended up doing basically daily profiles. And with, it's a trade-off, right? So if you do more frequent profiles, you're gonna run out of battery faster. And so in just the first 2.5 years of this pilot array in the area, we had over 5 times the number of winter profiles that existed in the World Ocean database. So that's every profile taken from the 1960s to 2018 was 5 times more just in those 2.5 years. So the amount of data that's coming out of this data set is very exciting, and to be able to get year-round full depth profiles is pretty awesome for that region. And so we can start looking at the water mass properties of Antarctic bottom water here. So I didn't put it into this talk, but each float is calibrated individually. And so the salinity sensors have a pressure dependency to them that you can compare to quasi simultaneous profiles taken from the ship that are calibrated with the hydrochemistry on the ship to get the best salinity data, which is important when you're looking at things like changes in salinity, subtle changes in salinity of Antarctic bottom water. And so we estimate the salinity accuracy on these to be plus or minus 0.002 PSU, which is of or equal to WOS Go Ship standards. So that's really good. And so you can start looking at the water mass properties, and you can start pulling out patterns. So you see this maybe strata in density. The colors here are the region of the basin, and the black is the northern part of the basin. So as you go from the blues to the reds, you're going eastward towards the Ross Sea, and the black colors represent the data farther north in the basin. So this is only for this is the average of these properties for densities greater than 28.3 kilograms per meters cubed. So a nominal Antarctic bottom water level. And so you can see maybe density sticks out a very strong pattern where you have much denser water in the southern part of the basin in those colors, and lighter waters in the northern part, which is not terribly surprising as you're mixing with the circumpolar deep water above as you're going around that circulation pathway. What you also see in the density is that it's fairly compensated in density in the southern part. So there's no real east-west pattern in the density. However, there is quite a strong one in the three other properties. So temperature and salinity is highest in that eastern part of the basin near the Ross Sea. So Ross Sea bottom water is generally a bit warmer and saltier than Adelie Land bottom water. And you also see warmer bottom waters in the northern part of the basin. The thickness is a little bit of a different story. We think it's mostly, so you do have this thicker bottom water farther west away from those two sources. And we think it's more related to actually just the configuration of the basin rather than anything real dynamical. And so this is the same information now plotted on a map and averaged in 1 by 2 degree little boxes throughout the basin. And the boxes here that are outlined in black have more than 5 profiles in them. So we have a bit more confidence in those averages. And you get the same story. So you get this warmer, saltier bottom water near the Ross Sea that's slowly or progressively getting fresher and cooler as you go to the west here. And then that the density, you see the densest bits right near the sources. So over in that southeastern corner of the basin and at near 140, near the Adelie Sill. But in general, it's fairly uniform in density along that southern part of the basin. And then there seems to be this divide in, especially in temperature and salinity around 60, 61 or 62 south. But, you know, so it seems to be quite warm to the north and quite light to the north and dense and cold to the south. But we don't have all that much data there. So, you know, it's hard to fill in that story with much confidence. And again, you see this thickening of the bottom water layer as you're going westward across the basin. And so you can get layer thicknesses of up to 900 meters. And it might be useful to say that for the density, temperature, and salinity, it's averaged below that isopycnal to the seafloor. So those are all full depth profiles, and the thickness, the flow only had to reach that isopycnal, and then you can still, so there's slightly more data that goes into those thickness averages than the other three, but it's all consistent. So if we look now we're gonna look in the densest, like a slightly denser bottom water. So now we're looking at neutral densities greater than 28.32. And we're looking along the slope. So we've averaged along that southern continental slope as a function of the maximum pressure that the float recorded. I should probably also say that it has each of the floats have a chain on them so that when they reach the seafloor, their buoyancy changes and they don't go smashing into the seafloor as well, but they get to within 2 or 3 meters of the seafloor. So what really stands out, at least to me in this picture, is that there's a lot more variability near 140 East. So in all of the properties, you see enhanced variability near 140 East. And that's where these two water masses or two flavors of bottom water are interacting for the first time. So you have Ross Sea coming from the east, Ross Sea bottom water coming from the east. And then that 140 is where you have most commonly a deli land bottom water flowing off the shelf there. So they're mixing and interacting for the first time here. Another thing that I want to point out in this figure is that on the Ross Sea side of the basin, so near 150, you actually see saltier bottom waters in shallower depths. So these red and blue circles here near 150 are in waters are above isobaths shallower than 3,700. So on the kind of mid slope range of depths. And then even as far as 140, even though there's more variability, those red and blue colors are actually saltier. So what that means is that there's a stronger signal of Ross Sea bottom water on the mid or upper mid slope, rather than in the deeper water. So if you think of it as a plume, the Ross Sea bottom water plume is not descending directly into the deep ocean, that it's actually hugging that continental slope at around 3,300 or shallower than 3,700.
And Annie,
yes.
The absence of that shallow signal west of 140, does that mean it's descended into the abyss by that stage? When it's sort of going diagonally downhill and then getting down to right.
It's a little bit hard to say because we don't have a huge amount of data in those shallower depths to the west. Like you can see here that it's still a bit saltier, but then by down here, it's pretty well mixed together. So I can't say with much confidence what I think I envision that the two flavors sort of get mixed together quite rapidly west of 140, and that it's hard to distinguish the two. And so this is looking now quite zoomed in near 150. So on the left is a map. The red line is the 3,700 meter isobath. The pink square is where a lot of the repeat hydrography that goes into these temperature and salinity plots that you'll see all over the place often come from these three stations, and then these two red ones from 1970. So on the temperature salinity plot on the upper right-hand corner is the same that I showed you earlier, where you see that freshening through 1970 to 2011. Oh.
We've lost.
What? Did anyone have any questions while we deal with technical issues? Yeah?
Trying to figure out those line variability classes. You know, you have the map of just the mean temperature, so you can see in the spatial plot of the dots is, you know, it's pretty 5 You have one of those just showing the standard deviation against 5 measurements.
I do.
That would help me like visualize what the
I do. It's not in this column. Yeah. Basically, you see a big right path of very near 140.
Like understand how much, what is the variability? Yes. Yeah.
Is it doing the same thing?
Context those historical.
So shutting down and restarting something else?
I know, but what I heard from my friend was so they just answer questions and then it comes back to it.
Yeah, I can show you.
I'll try restart.
But the variability, not near 140, it's very. But I don't have the number. This might actually help answer that question. So Paul was asking about how the variability or standard deviation compares to the mean that I showed in those maps for those of you who are online. And so this upper plot in the upper right is what I showed previously. So colors are the shipboard data, and you see that return of this strong characteristic Rossi salinity maximum at depth. And then the gray and the black are the deep Argo float profiles, as close as I could get. So in that box as well. The lower panel is a broader look at the region. So all of those circles, all the deep Argo data in that region. And so you can see, and that's over 2.5 years, you can see how big the spread is there. And it is somewhat comparable to the spread over, except you don't have this strong fresh signal, right? And so if you look at profiles that were taken shallower than that 3,700 meter isobath, that's this red, dark gray, and brown. So in 2018, 2019, 2020. So you again see this continued increase in salinity. And then in 2019 and 2020, especially for the deeper waters, or sorry, especially for the very bottom waters, you see that they're actually fresher than, so the 2020 deep profiles actually fresher than the 2018 shallow profile. I'm using shallow quite loosely here because it's shallower than 3,700. So some people might think that's quite deep. But you see this sort of start to hint that the Rossi bottom water is going that way rather than into the depths. We can do the same thing near 140, where we also have a lot of repeat shipboard hydrography. And it's a probably pretty messy plot, but it's similar to the one I just showed, where in the top right is just inside that box between this, I'm going to horribly mispronounce it, Hakure seamount and the continental slope, which has historically been where they found the strongest signal of Adelie Land bottom water. So the coldest and freshest waters there that they think come off the sill and flow through that little bathymetric saddle there. And you can see a hint of those waters also getting saltier between 2018, that gray line that is probably hard to see, and 2019, which is these black profiles that the floats took. And then if you look, and these values from 1969 or 70 are these red squares up here. So I actually argue in this paper that it's not really appropriate to include those in the very, very local trends, because it's quite possible but that they're picking up a signal of Ross Sea bottom water, and that's why you see that local deep salinity maximum. And so if you're thinking about trends, local trends of Adelie Land bottom water, that it's probably not appropriate to include those very old profiles. If you look at all of the deep Argo profiles in the region, you get the bottom plot. And so the green profiles there, the ones shown in green, are the ones only in this little bathymetric saddle. And the gray ones are from the broader region. And you can see that there's a lot of variability, but that the core of the Adelie Land bottom water tends to go through that little saddle there, in between the seamount and the continental slope. And so I mentioned earlier that there was a float that was doing daily profiling for quite a while. So there's actually about a month of near daily profiles taken by this one float as we worked out how to pilot it and make sure that we understood how to communicate with it while it's out there. And so this was from February of 2019. So kind of late summer, I guess. Yep. And it's the red dots in that map inset on the upper right-hand corner are showing a broader region of the profile shown in the larger map. So it's right by where we think Adelie Land bottom water or dense shelf from the Adelie Land coast is coming off and going down the slope. So it's again in between that seamount and continental slope. Okay, yeah. So each of the colored symbols on the map are a profile that the float took. And it starts its trajectory shown here in this southwestern corner. And then, sorry, I always confuse east and west. It's embarrassing. It starts in this southwestern corner and sort of makes this counterclockwise trajectory, nearly following isobaths, and then makes a sharp turn and comes back and does another sort of counterclockwise path that it takes. And that's that's for about 22 days it took to travel that. A caveat here is that we don't think that this trajectory is necessarily representative of the deep flow. Because it was profiling near daily, it's spending quite a bit of time in the upper part of the ocean. And so we don't actually think that that's what the deep flow looks like, but we do think that we can gain information about the scales of variability in the abyss from the data. So that's just to keep that in mind. And they're all these profiles, aside from the first 2 or 3, are full depth, and the maximum pressures are only span about 50 or 60 decibars. So it's almost completely along isobath or on the same isobath. So here in this green, can you see my pointer on here? Yeah, okay. Here in this green is right before the float turns around. And you can see that it had a minimum of temperature of about -0.5 and a minimum salinity about 34.83. A day later on that orange circle, which is only tens of kilometers away, and the very next day, you can see a very big change in the abyssal properties. So we see almost a whole 1/10 of a degree decrease in temperature and about 0.01 decrease in salinity. And that stays around or is sampled for those 3 days, that orange, light orange and purpley color. And we interpret this as a pulse of Adelie Land bottom water coming from somewhere along the Adelie coast, but appearing. And then we can't say whether there's a, if you imagine a blob of Adelie Land bottom water comes through, and if you had another profile in the same spot on day 4, that it would have already passed through, or that this next dark purple profile is over here and it's out of that little funneled flow of the dense Adelie Land water. But we do know that on scales of tens of kilometers and near daily, that you're having really large changes in abyssal ocean properties, which was kind of cool because you don't often get to see measurements like this because it's hard to take, and even on a ship, you're often moving to the next station, right? So you don't really get to just resample the same location over and over again. And another thing I think that comes out of this figure is that even in the 20 days over that small area, you do see quite a bit of variability in the bottom, in the deep ocean. So even this amount of spread in deep salinities is only a couple of days just right here. So there's a lot going on in the abyss, I think, especially in this location near where Adelie Land bottom water is formed. And so lastly, we use the shape of the TS profiles to infer the pathways. So we've done this sort of close examination near 140, near 150, try to work out what we think is going on. And then if we take a step back and look at the southern part of the basin, south of 60 South, and look at all the profiles from that 2.5 years, we can say if there's what we do is we say if there's a change in salinity between the 28.3 isopycnal and the bottom greater than 0.01, we think it's strong raw sea bottom water. If it's slightly weaker, we think it's maybe standard raw sea bottom water. And if it's even weaker, we think it's this kind of weak signature. But there is still, even in these very light, small pink triangles, there's still an increase of salinity at depth. And so there's still some suggestion that there's remnant raw sea bottom water there. Similar with Adelie Land bottom water, we say if it's very cold, it's a strong signal. If it's not as cold but still cold, it's kind of standard. And then there are some instances where you actually see raw sea bottom water sitting above Adelie Land bottom water, sort of like that. And so you can actually use those data, make a map of where the strongest signatures of these different water masses are, look at how they are spread out along the southern part of the basin, and you can get a more data based schematic, which has all the different color arrows on it. But we think, the thicker the arrow, we think is the main pathway. So we actually envision raw sea bottom water coming up along this part of the slope, but we do see that there is indeed some that goes into the deeper ocean, and whether that's driven by eddies or funneled flow through canyons or some sort of tidally driven process that's bringing raw sea down off that main pathway hugged against the slope. We can't figure that out from these data. And, you know, we do see this hint of it coming around the northern edge of that seamount, and strong Adelie Land bottom water flowing again through that little bathymetric saddle there south of the seamount, but some also veering off to the northeast. And then we kind of envision it's all mixed together and just sort of cold. And so in conclusion, we can successfully map the properties throughout the southern part of the basin, especially, and that we do see a return of the deep salinity maximum associated with Rossi bottom water, and that it spreads as far east as 130 east, and that the pattern of those water mass properties implies the main pathway of Rossi bottom water is actually hugged up against the slope rather than directly into the abyss. There's really enhanced variability near 140, and that's not all that surprising given that's where Rossi and Adelie Land bottom waters are interacting for the first time. The strongest signal of Adelie Land bottom water seems to be channeled through that bathymetry saddle between the seamount and the slope. Those 1969 profiles need to be flagged as with caution when looking at very local trends. And there's high frequency variability on the scales of tens of kilometers and days near the slope. And then we can make this pretty map with different color arrows on it, which has more information and is based on more data than we've been able to do in the past. And that is from 2.5 years of the data, and the array still exists, and it has been reseeded with a few more floats. And so there's another almost 2 years of data existing now. So we'll be able to look at things like seasonality and stuff like that. So I think it's a great data set, and I hope you learned something from it. Yeah, and there's lots of information in that paper.